Hi guys, my name is Artem Lenyov, the author of the PULsE software. If you are watching this video, you're probably familiar with laser flash analysis and the challenges users are facing. To help you out a bit, I have developed this cross-platform open source software which you can download from the PULsE website. If you have Java 11 installed on your operating system, it's easy to run it by just double-clicking on this jar file, which opens a splash screen with the logo and the version number. It takes some seconds to load. And then finally a graphical user interface appears consisting of 4 internal frames and a top menu used to do operations with the data. Obviously no data shows up since this needs to be loaded first. So navigate to the main menu, click on File, then Load Heating Curves, then select the location for your data files. In this example, I'm going to show you what to do with data for a pyroceram sample. So we select all files here. And just to make sure we're on the same page, PULsE does not connect to the instrument and it does not know anything about the firmware protocols. But every commercial instrument runs on a software capable of exporting raw data in a text format. This exported data is dealt with by PULsE and is loaded into the software here, with each file generating a corresponding task for the thermal parameter extraction. Obviously you need to select a way to treat this data. In order to do this, navigate to the main menu, click on Calculation Settings, then click on Hit Problem Statement and Solutions, which opens up another frame where you can see a list of the model statements available that have varying complexity. And in this case, we're just going to use the most simple model, which is suitable for opaque materials, the classical 1D model. And after you select it, there's some background calculation going on. Once you have selected the problem statement, PULsE will automatically select the most appropriate finite-difference scheme solver for that specific problem statement. In case if you want to amend that choice, you can select an alternative from the list on the right. If you want to change the discretization for that specific case, you can navigate to the grid properties and then select a different value, for example for the grid density. Select a lower value for the grid density if you want to maximize performance. Select a higher value for grid density if you want to maximize accuracy. At this stage, it's extremely important that you check that the problem statement as well as the problem parameters are selected appropriately to the experiment at hand. For example, it's important to check that the baseline is selected appropriately. And in this case we have the linear baseline which was chosen by default, but it's also possible to select a flat baseline or an oscillating baseline. In this case we want to stick to the default. Next, you can choose that the sample thermophysical properties are also reasonable. For example, you can check that the sample thickness is in accordance to the sample thickness from your experiment. The thermal diffusivity and adiabatic heating parameters are selected automatically, so you do not want to change those. However, if you want to conduct calculations assuming that you have adiabatic boundary conditions, then you need to change the heat loss factor from 0.2 to just 0. So you just click on this value and then you just type the value that you want and then press enter to commit the changes. Immediately upon committing these changes, you will be able to see that after clicking the plot time temperature button, the changes have been reflected on the plot. For example, in that specific case, you see that the time temperature profile is reaching saturation and is not decreasing anymore. Now, because we know that there is a heat loss factor in the pyroceram sample, we want to change it back to the 0.2 value. Now, if you click on the plot time temperature button again, you will see that you now have a negative slope on your time temperature profile. There are other options to change. For example, the pulse shape can be changed to match the pulse shape from your experiment. In that case, when no pulse information is available, PULsE will start with the default value of the pulse width, which is 1.5 millisecond, and also it will load a rectangular pulse. You might have noticed that the actual pulse shape, which is plotted on the left, is different from the rectangular pulse, and it's more like a trapezoidal pulse. This is due to the discretization parameter. In that case, the time step is not sufficient to fully reproduce that pulse. You can change that by changing a different value of the grid density, and you can set it to, for example, 60. Then after you press the plot button, you will see that the pulse is more in accordance with the rectangular shape that you have selected. But in that specific case, you do not need to have a very accurate pulse, so you can change it back to 30. After you're done, just press on the cross here, and then you're almost all set. So for each task, you have selected the problem statement, and therefore you are able to see the blue curve, which represents the solution of that specific problem. But something is still missing because the status is shown as incomplete. You can see what is missing exactly when clicking on any of the tasks and then selecting the what is missing button, and you will see that the optimizer is not specified yet. To select the optimizer, navigate to the calculation settings menu, then parameter estimation method and settings. A new window pops up where you can choose from a list of available optimizers. By default, the Levenberg-Marquardt optimizer is selected when you have the objective function set by the sum of squared residuals. This is the most common choice, and it also offers the most adequate performance, so it's the fastest option for the least squares. There are also alternative options, for example the BFGS, which stands for Broyden-Fletcher-Goldfarb-Shannon quasi-Newton method, which is an alternative method working with arbitrary objective functions. So for example, if you click on the calculation settings, then statistical analysis, then optimizer statistics, you might see that in addition to the standard ordinary least squares, there is also an option to select the absolute deviations. This is an optimizer statistic which is robust to outliers, so sometimes this is preferred over the least squares approach, but in this case we're just going to stick to the default. Now you might also see that there are two tables below where you can select which parameters you specifically want to optimize. Now each problem statement usually has a preset parameters for optimization. For example, the 1D problem statement just has 3 parameters, which include the thermal diffusivity, adiabatic heating, and heat loss. Now if you want to include something else, you can select from the table on the left, and for example you can choose to have the time sequence shift if you suspect that there is a mismatch between the pulse time counting and the main detector time counting, and then you just press on this right button here in the middle, and then you have this parameter in the optimized parameters list. Now we do not want to do this right now, so we just move this specific parameter to the left. In addition, you might also see that there is an option to change the upper and lower bounds for calculation, but this specific option is not compatible with the Levenberg-Marquardt implementation because it changes the number of data points. In case if you want to do this, it's better to select the BFGS optimizer and whatever objective function you prefer. Now, for the super advanced users, there is also a table at the bottom which lists the different technical parameters for the optimizer. Usually, you do not have to change any of those, only if you want to dig very deeply into the mathematics of optimization. So then if you are done here, just press cross again, and then you will see that you are back to the tasks manager and all the tasks are now listed as ready. This means that you can start the parameter extraction. Now, for example, you can do this as a single task execution or also batch execution. In that specific case, I'm just going to select a problem statement, a task. For example, this one, task number 20. And then I'm just going to ask PULsE to execute that specific task. So I just right click on this task, then a drop down menu appears and I select the execute from that drop down menu. And you will be able to see that something is being done. So the search statistic is changed and also the status has just changed to done. This has taken a total of 1.5 seconds. So this is pretty quick, and you now also have the result for that specific task at the bottom right of your screen. So we now see that for the task 20 at the temperature of 300 degrees Celsius, our thermal diffusivity equals to 1.22 and 25. So you are also able to gauge whether the problem solution for that specific task is a good fit to the experimental data at hand. So it seems that actually the data looks quite good, quite close to the problem solution, so it's probably okay. And I'm just going to show you something else that you're able to do. You can select another task and then tick to select the verbose log option for that specific task. Now, if you click on the execute button again, you will be able to see in real time how the parameters are being optimized. For example, it takes 16 steps to arrive at converged values for those parameters, and that means that there is actually a buffer which is being filled during the optimization, and this buffer has a certain size. When it is filled up, then some checks will be processed to see whether the parameters have reached the convergence. And you can also change the size of the buffer by navigating to the calculation settings and then clicking on buffer size. By default, a value of 8 is used. Now it is time to do the calculation for the rest of the tasks, and because we have a total of 47 tasks, that would take ages to go through manually through each task. So what we are going to do is to run batch calculation. In that case, we are interested in clicking on this green man button here, execute all tasks. And as soon as we click it, the software will use available CPU cores to run threads in parallel. And we just try to do this. Now you see that part of the tasks have been queued and others are in progress, others are already done. That means that some of the tasks are being executed in parallel, and the number of tasks that can be simultaneously executed is given by the number of cores available on your machine. For example, my laptop has 4 independent cores, but it has also 2 independent threads at each core. So this means that PULsE has identified the laptop has a total of 8 cores, and the number of threads that can be used within the software is equal to 6. When this calculation is done, you might have also noticed that the CPU usage rises to high values of maybe 70-80% or maybe even higher, and this is directly reflected from the fact that the different cores on your machine are being used for calculation. And also keep a watch on the memory usage statistic here, because if it reaches values of maybe 80 or 90%, which sometimes happens if you have a very computationally intensive task at hand, then you might also experience some problems with your laptop freezing, or maybe your PULsE program quitting unexpectedly, but that happens very rarely. So that doesn't happen very often at all. And so now, after all tasks have been done, you might also see that the result table is also filled up, and you can also check which task actually corresponds to which result. So when you click on some task from the task manager, the corresponding result will also be highlighted, and also you will be able to check that the time temperature profile is adequate. So if you are happy with the way your results look like here, you can, by the way, also check the search statistic, and you can also filter this table to see which task has the least search statistic. So that means that the fit is actually better for that specific task, and which of them has the worst search statistics. So for example, I see here that there's a 1.5 times 10 to the minus 3. So this is maybe not ideal, but when I look at it, I see that it's actually quite good. And I can also see that there's a graph of the residuals. So if we maximize this window, we can see that there are some residuals here showing an unexpected outlier at the beginning. And we can also check the histogram for the residuals to see that the results are adequate. So if we click on this button here, this allows us to see the histogram for the residuals. And as I just said, there are some outliers which are also present on this histogram at minus 0.8 and minus 0.6 and also at 0.2. But what we're really interested in is in the bulk of the residuals, so in the way this bulk of the residuals is distributed. So in this case, we can just zoom in onto this part and also increase the number of bins. And now I'm able to see that actually the residual histogram appears more like a Gaussian histogram, probably. Well, actually the mean for the residuals appears to be slightly shifted to the right, so I will say something about this, what to do with that if we want to maximize accuracy. But right now I'm just going to say that if you're looking at the tail of that solution, you will be able to see that the solution is actually systematically higher than the data points here in this region. So I will also touch upon this in the next video, probably, to say what can be done in order to eliminate this effect. But for now, this is just to give you a brief feeling of how actually PULsE works. So after this is all done, you can navigate to the preview button here on the button panel for the result frame, and you can click on the preview button, and you will be able to see that the different results for the thermal diffusivity are plotted in the same graph. And because the experimental data includes shots, a series of shots at each temperature, at each test temperature, you are probably also interested in merging data points which refer to the same temperature. In that case, also navigate to this menu on the bottom right and then select the Merge Auto. And then you need to specify the averaging window, which will be used to identify data points which lie in the same sequence. So in that case, I'm just going to select a value of 1 for the threshold temperature difference between the data points, and therefore subsequent data points, subsequent shots will be grouped into one group if the difference between the temperature of this and the subsequent shot is less than the averaging window. So I click OK. Then you might see that something has happened to the table below. So it has now changed to the view for the mean values, and also an error value appears. So this is actually the real error, which is calculated given the confidence level of 0.95, and also the span of the error is actually equal to the actual length of the confidence interval. In order to plot the graph with the mean values, you click on the preview button again, and then you're able to see that the actual graph now lists the errors for each temperature. Now you click close if you are happy, and then you return back to the task manager. After all your tasks have been done, you are now interested in saving the results of your calculation. In that case, you need to look back on the results frame, and you want to select the Save button from the button panel. Click Save, and then select the location for your result table to be stored at. Then select the appropriate file format for your results. You want to choose the CSV file format if you need to use a plotting program afterwards to visualize your results, for example GNUplot or Origin. In that case, choose CSV. If you want your results to be nice looking, to have a visual representation of the results, you just select the calculation results in HTML. Now just save it on your desktop or wherever you want. Then I'm just going to show you how it looks like. So this file that has been generated just now contains a table with the mean values for the parameters that have been listed in the result table. So that's just the ID, the temperature, and the thermal diffusivity. And after this table, you also have another table with the individual parameters for each specific task. Now, you might also want to change the format of the result table. In order to do this, you need to go to the calculation settings and select Change Result Format. And in this same way that you have changed the optimization parameters, you can change the output of the result table. So for example, you can select to have your, let's say, bio number in that table as well. So in order to do this, just select this bio number from the table on the left, then click on the right button, and after you're done, just press on the commit button. But in that specific case, we will not do this because this change in the result format usually works well just before the calculations are done, not afterwards. So if you want to change the result format, the best way to do this is to click on the is to change it, and then click on the execute all tasks again to have the new results. Otherwise, you will have some unexpected values of the parameters in your result table. Now, after this is done, you have your result file saved. Now, you might also want to export the data for each individual curve. In order to do this, you might press just the export current to export the currently selected task, or just the export button. And in that case, a dialog opens which allows you to select which of the options you want to save. So for example, the solution, the raw data, the data points that have been loaded from your files, but they can be saved in a more convenient format. The logs, for example, if you have the verbose log option, or you can just create subdirectories for each specific task to allow better navigation in future. Similar to the result table, you also select the appropriate file format, for example CSV if you want to replot it further, and you select the project name. So in that case, I'm just going to type PULsE. You can see that the export path has changed to reflect the project name. I also want to export it not to the root directory but to the documents. In that case, I just select the document folder and then press open, and then I can see that the export path has changed. I press export, so it's just taking some seconds, and then I can navigate directly to the folder which has just been created, and all these different subfolders correspond to the 48 tasks that I have uploaded. And the null here at the beginning of the folder name means that the sample name has not been specified. So if I later want to visualize the heating curve, I can, for example, if I'm running Linux, I can open the terminal, then enter gnuplot, and then type plot heating curve 0, and using columns 1 and 2 with lines, and there we go. So that's the solution that has been generated with PULsE, and you can also see where the raw data is. So in that case, I'm just going to add this raw data, and that's it basically. So this is your curve there behind those points, and those are the raw data. Thank you for watching. If you want to learn the different secrets of PULsE, I would be happy to tell you about them in subsequent videos. Just please leave a comment at the bottom of this video, and if you like this video, just press thumbs up. Thank you.